decades in the software industry, he has worked as a programmer, analyst, designer, and researcher for organizations such as Lawrence Livermore National Laboratory, the Boeing Company, and Rockwell Collins Inc. At Constructs, Mr. Steve Tockey applies his deep expertise in object-oriented development, model-based requirements and design, software engineering economics, development processes, project management, estimation, and software quality to help clients adopt best practices throughout software development and maintenance. He holds a master's degree in software engineering from Seattle University and a BA in computer science from the University of California, Berkeley. He is a certified software development professional and has chaired the certification committee of the IEEE Computer Society. Mr. Steve Tockey has also been an adjunct professor at Seattle University and is the author of 2 influential books, Return on Software and How to Engineer Software. Today, he will deliver his keynote address on the futuristic theme, the top 5 challenges in software development. Ladies and gentlemen, please join us in welcoming our keynote speaker, Mr. Steve Tockey, with a warm round of applause.
Thank you very much. Let me share my screen first, and then we'll start the presentation. Come on. Share entire screen. Yes, share entire screen. Okay. Okay, so hopefully everybody can now see the presentation. Top 5 challenges in software development.
Yes, sir. It is visible to us.
Okay, great. So the goals are for you to be aware of how poorly most software projects actually perform. I want you to understand the biggest causes of software project difficulty, and I want you to know effective remedies that you can use to solve those problems. The roadmap will be to talk about what software project success really is. I want to talk about typical software project outcomes based on studies of thousands of software projects. And then based on some independent data, some of my own data, I want to talk about the top 5 causes of poor software project performance. And then I want to give you a high-level get-well plan. Of course, there are more details underneath. We can't go into all the detail in the limited time we have, but I want to point you in directions that you can go to start fixing problems on typical software projects. Oh, by the way, I will be making the slide deck available. I'll make a PDF when we're all done here, and I'll email it to Dr. Anurag Singh, and he can make it available to all of the conference attendees. So you will be able to get a copy of the slides. That won't be a problem. So I want to start by talking about software project success. Now, this is a definition of software project success that was created by a guy named Tom DeMarco, who's very famous in the software industry. Tom defined software project success to be 5 things. Does the software project finish on time? Does it finish within budget? Does it deliver everything it said it was going to deliver? Does the product that got delivered have appropriate quality? And then finally, and very importantly, is the team stronger? Are they better off because they did the project, not weaker because they did the project? That the people didn't get burnt out, people didn't get sick. Again, they're stronger, they're better, they know more. They're happy to go to another project instead of being burnt out from working too many hours of overtime. And so first of all, I want to make sure that everybody understands that this is the definition that I use when I talk about a successful software project. Now, very quickly, we need to talk about the difference between a successful project and a successful product. A successful software product sells lots of copies, has lots of customers, the customers are happy, and the company that made the software gets very rich. that's a successful software product. Now, a successful product is not always the same as a successful project. You can be a successful product without being a project success. But certainly a successful project has a higher probability of leading to a successful product. Okay. What typically happens on software projects? Well, again, based on studies of thousands and thousands of software projects, the latest data shows us that 18% of software projects fail to deliver any usable software at all. In other words, approximately 1 in 5 projects spend lots of time, spend lots of money, and never actually produce anything that's useful to anybody. So clearly, they're a net write-off. Clearly, there's no value. There's no return on investment there. Now, if we consider the remaining projects, the remaining 82% of the projects that do actually deliver usable software, the average is that they're 42% late. If you thought it was going to be a 10-month project, chances are more likely it was a 14-month project. And also 35% over budget. If you thought it was going to cost $1 million, it is more likely to cost $1.35 million. Now, in spite, I mean, it's bad enough that you're 42% late. It's bad enough that you're 35% over budget. But that's not even telling us the whole story, because in spite of being late and over budget, you're 25% under scope. 25% of the things that you said you were going to deliver on your project never got delivered. So just being late, just being over budget isn't telling the complete story. We're late, we're over budget, and we didn't deliver everything. And finally, of the software that does get delivered, it's riddled with defects. It's very buggy, typically, software. Now, it's one thing to look at these statistics in terms of 42% late, 35% over budget. But what I want to do is turn that into real money, okay? So I looked up recently, and in 2024, 675 billion US dollars were spent around the world on software. That's the best estimate that I've got, okay? So that's the total amount that was spent on software projects in the year 2024. Now, 18% of that is $122 billion. And the reason I say at least $122 billion in failed projects is because we actually know that not all projects are equally likely to fail. We know from history that there's a correlation between likelihood of failing and the size of the project. The larger projects are the ones that are more likely to fail. So it's not just 18% of all projects, well, yes, by true number, but of that 18% of projects that do fail, they tend to be the larger projects. And what that means is that 18% of $675 billion, or $122 billion, is actually an underestimate of the true value of the failed projects. Okay, now if it's only $122 billion in failed projects, then the 42% late adds on another $144 billion in cost overruns. And the 35% over budget adds in, the 25% under scope takes out another $82 billion in scope underruns. So my point here is that while $675 billion got spent on software last year, that the functionality that got delivered, those people who were paying the money to get the software should have expected to pay only $328 billion for the software that they actually got delivered. In other words, if they had got all of the software for the $675 billion, maybe that would have been okay. But they paid the same $675 billion and only got $328 billion worth of software out of it. Now, we'll see later in the presentation where even the $328 billion is actually too high, that theoretically they could have got the same amount of software that actually got delivered for roughly half of what of the $328 billion. Now, the point here is we're talking about billions and billions of US dollars. This is too much money to ignore. It's simply too much money to ignore. If I just say, oh, projects are 42% late, that's easy to ignore. Projects are 35% over budget. Oh, that's easy to ignore. But over $300 billion, that's something that clearly I don't think we can ignore. So what I want to talk about now are the top 5 causes of poor software performance. Now, I have data, I have my own data, I have data from other sources that supports that the number one reason that software projects get into trouble is because of vague, ambiguous, and incomplete requirements. The number 2 problem is inadequate project management. Now, we'll go into these in more detail later. The number 3, the number 4, the number 5, I don't have actual data, but based on nearly 50 years of experience involved in software projects, my experience suggests to me that the number 3 reason, uncontrolled design and code complexity. The complexity in the product gets out of hand and people just can't understand it anymore. Number 4 is overdependence on testing, and number 5 is not an initial development problem, it's a long-term maintenance problem. And that's that in spite of you thinking that your code is self-documenting, the reality is that code cannot be actually self-documenting, which affects the maintenance of the code. So again, I'll go into all of these in a little bit more detail. So let's start with cause number 1, vague, ambiguous, incomplete requirements. Now, the root issue here is that most projects are discussing requirements in a natural language. You're discussing requirements in English. You're discussing requirements in French. You're discussing requirements in Hindi or Malayalam or Kannada, whatever. Whatever natural language you're using to discuss the requirement, natural language is inherently ambiguous. The same word in the language often has different meanings, and different words in that language often have the same meaning. And so simply meanings of words causes some ambiguity. And so if you notice on the bottom here, one of my favorite, if you can see my cursor, one of my favorite examples of a ambiguous software requirement, the system shall detect a 1/4-inch defect in a pipe section. This is about software that runs in a device that goes through a chemical factory, and it inspects the pipes to make sure that you don't have a problem in the pipes in your chemical factory and it's safe to run your factory. There's a particular company in Paris, France that builds these devices, and this was a real requirement out of some of their software. Now, the problem is that there are about 32 different but valid interpretations of the word detect alone. There are 3 different valid interpretations of the word a. And so if I have about 32 and about 3, I'm now talking about 96 different valid interpretations of the first 2 important words alone. There's another 3 interpretations of 1/4-inch. There are another 32 or so interpretations of defect, and another 20 or 30 interpretations of pipe section. Now, what that means is that any person, when looking at that statement, can interpret it in as many as 9,126 different ways. There are at least 9,126 different valid interpretations for that one requirement statement alone. Now, the problem is that the person, the product owner, the domain expert who stated that requirement meant one of those 9,000 interpretations. But what's the probability that the software people had exactly the same interpretation? And the answer is only 1 in about 9,000. And what is the probability of a different interpretation? Well, it's about 9,000 minus 1 divided by 9,000. And so if you know anything about betting, the chances are you lost that bet. The other issue here is verboseness. It takes too many words in a natural language to get down to the level of precision that we need in order to communicate. So that's the underlying problem. Now, I'm going to actually talk about a solution here. And so a potential solution for solving the vague, ambiguous, incomplete requirements problem is to use something called acceptance test-driven development, ATDD. Or there's a very close cousin of this called behavior-driven development, or BDD. Now, the whole trick to understanding ATDD or BDD is before anybody writes any software, we get a group together that involves the developers, the domain experts, the product owners, and the QA test people, and everybody agrees before any code is written what test cases, what acceptance test cases that code needs to pass in order for everybody to agree that the code satisfies the intent of the statement, the intent of the user story, as it were. Now, the reason that this actually works is because if you look over here on the slide where we talk about the structure of a typical test case, okay? If you write a test case, they always have a very similar structure, which involves starting with some initial configuration and some stimulus, with the arrow being interpreted as we expect to see. Given this input, given this stimulus, we expect the software to produce this result. When asked to compute the square root of 9, the square root function should return 3. That would be an example of a test case. Okay, but what I want to point out here is that the arrow, when we consider it to be a test case, the arrow is interpreted as we expect to see. When given input that looks like this, we expect to see output that looks like that. Well, all I'm going to do is just reinterpret that arrow away from we expect to see and redefine it to mean the system shall produce, okay? And so when given input that looks like this, the system produce output that looks like that. All I've done is change what you thought was a test case into what really is a requirement. And that's really the whole point here, is that by writing the requirements in test case language, we know that test case language is unambiguous. And so we're writing the requirements using test case language that what appears to be a test case is actually merely a requirement. It just happens to be written in test case language, and we know test case language is unambiguous, so we solve the ambiguity problem. Okay, so that's one way of solving the ambiguity problem. The other way, if you're familiar with the idea of blueprints, if somebody's going to build a house, if somebody's going to build a building, we don't give the builder an English description of the house to build. We give them blueprints, we give them drawings, and there's a language about how to describe a house or a building to be built, including a left-hand door means the door swings open to the left, and a right-hand door means the door swings open to the right. Now, it's hard to see on these particular house drawings, but there is a bathroom, a WC right here, and there's a line and an arc that shows which way the door opens. That if you translated that to English, it would say that the main floor guest bathroom shall have a door. That door shall be a left-hand door, and that left-hand door shall be oriented so that the hinges are on the south side of the door frame. Now, what I mean there is that on the drawing, there's a line and an arc, and that one line and arc on the drawing stands for what literally is a half a paragraph in English. And so there's a language, there's a special dialect of the modeling language UML that we can use to describe functional requirements in a very precise, very concise way. And clearly, we don't have time to go through this in very much detail, but there is a dialect of UML that we can use to make blueprints of software requirements. The point here is I'm giving you QR codes because, as I said, we don't have time to go into it here, that there are some YouTube videos that you just, QR codes, and you can watch 4 YouTube videos about this dialect of UML, that we can solve the ambiguity problem and we can solve the verboseness problem by expressing the requirements as very concise drawings, okay? A lot more depth there, we just don't have time. And so the important point here is that the people who design and build houses gave up trying to describe houses in a natural language more than 100 years ago. That blueprinting language for houses was developed more than 100 years ago. So what makes you think you can successfully describe something, your software, that's orders of magnitude more complex than a house using a natural language? This is just arguing for the need for a blueprinting language for software requirements. The other thing is that most people claim that the requirements keep changing. Well, in my experience, it's not an issue of the requirements are changing. What the customer wanted when you first heard them say in English, what you thought they meant is not what they really meant. We are blaming them for changing their mind, when in fact their mind didn't change. It's just being clarified. What they wanted was the same all along. We just misunderstood what we thought that they wanted. Okay. Number 2, inadequate project management. Again, this is a very deep topic. We don't have a lot of time, but poor goal alignment. The priorities on the project keep changing. The priorities are driven by the last customer who complained the loudest. Poor project planning, not decomposing the work sufficiently, overly optimistic estimation, unrealistic externally imposed deadlines. You can read all of these problems as well as I can. And so, for example, real data from a real organization. Each of the X's on the X-axis, what this represents is how far in advance of the completion that the project manager was predicting the project would be completed. What's showing up on the Y-axis is how long after they predicted did it actually take to finish the project. And so any X that's on that line corresponds to perfect estimation accuracy. I told you 50 days in advance that we were going to finish 50 days from now, and 50 days from now we finished. That's perfect estimation accuracy. But notice how few of the X's are anywhere near that perfect estimation accuracy. This X right here, if you can see my cursor, amounts to somebody saying that we'll be done next week, but it literally took them 9 months after they said we'll be done next week, and 9 months later they actually finished. And so this is horrible estimation accuracy. This is very definitely overly optimistic estimation. There's a concept called the cone of uncertainty, which basically means early on in the project we just can't know everything. And this is the idealized cone of uncertainty. But what I want to show you is that, in fact, in several organizations, we've actually measured their cone of uncertainty. We can measure the amount of uncertainty. And here's an example of the measured uncertainty in a particular organization. Here's another measured uncertainty in another organization. Here's another, here's another. With the point of this being is that every organization's cone of uncertainty is actually different. There isn't a standard cone of uncertainty. That idealized one that I showed you first was symmetric about plus and minus. This describes in the real world that there's a chronic tendency to underestimate by a lot. The idealized cone of uncertainty, as expressed, is hopelessly optimistic for most software organizations. The worst case outcome on the idealized cone of uncertainty is better than what you're seeing as a good case in the real cones of uncertainty. So again, to move on, the QR code that's down here in this corner will take you to a YouTube video titled A New Look at the Cone of Uncertainty, which goes into a whole lot more detail about what the cone of uncertainty means, how you calculate it in organization, and it gives you access to a free tool that if you collect the data that we need, you can actually put the data in and calculate your own organization's cone of uncertainty and use it for planning your projects. Okay, number 3, uncontrolled design and code complexity. The issue here is partly structural or syntactic complexity. There's a measure called cyclomatic complexity about software that says how many decisions are being made in that chunk of software. And so if you look at the little fragment of code that's over here, the flow chart for that same code, what you'll notice is there are 1, 2, 3, 4, 5 decisions being made in the code. Well, cyclomatic complexity is defined as that number of decisions plus 1. So the cyclomatic complexity of that little code fragment is 6. But what we know here about software is that defects in software are not uniformly distributed in the code base. They're not random. They don't appear kind of at random. They cluster, and they cluster around complexity. Higher cyclomatic complexity means higher defects. And so more complex code is harder to understand. More complex code is more of a defect magnet. Okay, and so the point here is if you don't control complexity, then it gets incredibly complex. Very simply, by the time the cyclomatic complexity of code gets over about 40 or 50, no human on planet Earth can actually understand that code. And yet we routinely see functions in commercial product code bases that have cyclomatic complexities between 150 and 350, meaning that clearly no human on planet Earth can really understand what's going in that code. It is guaranteed to have defects. Semantic complexity is not structural, means that we can look at the code and just interpret it. Semantic complexity, if you're familiar with the SOLID principles, S-O-L-I-D, single responsibility, open, close, Liskov substitutability, it's about the meaning of the code, not the structure of the code. And this kind of analysis we can't do using a code quality, a static analysis tool. This is analysis that needs to be done by hand. And so there are opportunities to control the complexity. This is the problem. We're not controlling the complexity. We're not managing the complexity. The code becomes a defect magnet. Overdependence on testing. The idea here is the earlier you make the mistake, the later you find it and fix it, the exponentially more expensive it is to fix that defect. Okay. 2 drivers of the cost increase. 1, how long has it been since I last understood this code well enough to work with it, if ever? The longer it's been since I've worked with it, the longer it's going to take me to become familiar enough again to work with it. The other aspect is these cascading consequential decisions. Requirements are essentially decisions. For every requirement, there can be many design decisions derived from that one requirement decision. For every design decision, there could be many code decisions derived from that one design decision. Because that one code decision, it can lead to many structural test cases, white box test cases. But further, for each of the requirements, we would then have functional test cases. And so notice how this is kind of a tree. It's one to many, then another one to many, and another one to many. And so if all I had to do was change a code decision, maybe I have to change a test case or 2. But if what I have to do is change a requirement, that cascades into changing more design, exponentially more code, exponentially more test cases. So that's the idea. Now, if you look at a typical software organization and ask the question, where are the defects coming from? you'll find that 56% of the time, the defects are coming from vague, ambiguous, incomplete requirements, okay? 27% of the time, it's poor design, wrong algorithm, wrong data structure, wrong architecture. Only 7% of the time is it truly a code-injected defect. And so what this tells us is 83% of defects exist before the code corresponding to that requirement and that design is actually written. And so the question to ask here, when do most software organizations even start to look for defects? And the answer is after the code has been written, when you're testing the code. But 83% of the defects existed before that code was even written, meaning that the average cost to repair the defects is massively high, okay? And so, again, we're rushed for time. We don't have a lot of time to talk about this, but one of the things we can do is measure how much time on the project is spent fixing mistakes that were made earlier in the project. Talking about refactoring, I'm not talking about the customer changed their mind. I'm talking about somebody wrote some wrong code, we found the code being wrong, we had to go back and fix it, and how much time is being spent going back to fix it. And when we measured that in 5 different organizations around the world, 350 developers in Beijing, China, the as measured rework rate was 57%. 57 out of every 100 hours that they spent on the software project was fixing mistakes that were made earlier on that same project. 50 developers, blah, blah, you can read through this, but we're calculating a weighted average, weighted by the size of the organization. It would appear that about 61% of the labor hours being spent on software projects is this non-value added rework, okay? And so this is why I say that we can in fact cut rework significantly. We can get rework to be under 10%. And so if I can reduce rework from 60% to 10%, that means basically I'm twice as productive. And that's why I said earlier that the $328 billion that we spent on software, we could actually cut that in half. And yes, we can cut it in half by cutting the rework, okay? And so rework is not only the single largest driver of cost and schedule in a typical software project, it can be larger than all other cost and schedule drivers combined. Okay, so we think of the job of a developer as doing some requirements work, some design work, some construction work, some testing work, and we think that that's the developer's job. But my point here is that if you account now also for the 61% rework, that the requirements, design, construction, and testing work can't be any more than 39%, or roughly 60% rework, 40% value add, okay? Because they are doing the rework, we know that, but the rework doesn't contribute directly to satisfying the project's goals. And so again, the #1 driver of cost and schedule on a typical software project is rework, okay? But defects are not only about the quality of the product. What we need to do is understand that the defects are actually about the quality of the process that's being used, okay? Rather than reading the entire quote, raises questions about the quality of the development process. That's Martin Thomas. The real value of tests is not that they detect defects in the code, but they detect inadequacies in the methods, concentration, and skills of those who design and produce the code. The defects are there because your process allowed them to be there. They're not just quality in product issues, they're quality in process issues. If you don't want the defects to be there, you need to change your process. So we can find the defects earlier when they are cheaper to fix, and here are some things that you can do. The acceptance test-driven development that I mentioned earlier, behavior-driven development that I mentioned earlier, model-driven development that I mentioned earlier. All of these things are things that would allow us to find defects earlier, allow us to fix them earlier when they're cheaper to fix. By doing model-driven development, by controlling design and code complexity, we can reduce the growth rate. Yes, it's the same amount of time, but the cost growth is not as much. And there are things that we can do, like model-driven development, like using standards, templates, and checklists, that will allow us to even avoid making the mistakes in the first place. Now, the QR code in the lower right-hand corner here is to a YouTube video, Rework How Healthy Is Your Software Process, that goes into this topic in much more detail, okay? And then finally, code cannot be self-documenting. The issue is that you can go get some arbitrary chunk of code and you can walk through it, you could step through it in a debugger, you can figure out what it does, but what is it intended to do? You call it a bug, I call it a defect. It's merely a difference between what the code was intended to do and what the code actually does. The code will only ever tell you what it does. It can't tell you what it was intended to do. The other thing about the code is, why does the code look the way it does? Does this code have to look this way? Does this code happen to look this way? Now, the point here is that if we look at all of the money spent on software, 20% of all the money spent on software is spent building new systems that never existed before. 80% of the money is spent maintaining existing systems. So if somebody came up with a way where they could cut new development in half without affecting the maintenance of the code that got produced, that would save you 10% of the overall cost of ownership of that code over its entire service life. Now, on the other hand, if we could do something that would reduce the maintenance by 50%, that would save you 40% of the lifetime cost. The point that I'm making here is that you spend far more money, you have more leverage about controlling the cost of code when you're maintaining it. And so the requirement specification is what tells us what the intent of the code is. Design documentation should be more about why the code looks the way it does than how the code looks. Don't tell me how the code looks, tell me why it looks the way it does. And that requirements and design documentation will significantly reduce the maintenance costs over the lifetime of the code. Okay, so quickly, the high-level get well plan. For issue number 1, avoid natural language requirements. Use acceptance test-driven development, use behavior-driven development. They're essentially close relatives of each other, with something called functional coverage criteria that we don't have time to go into here. You can send me an email and we can talk about it that way. I'll give you my email address later. Or the model-driven development. Strengthen your project management. In particular, understand how to estimate better. There's something in the Agile community called velocity-based sprint planning, which significantly improves your ability to estimate and plan. Deliberate planning and tracking. Acknowledge the inherent uncertainty in your software projects. Manage the inherent risk. Measure and control design and code complexity. If you have an Agile project, if you have a definition of done, part of the definition of done should be essentially constraining those structural complexity metrics. Look for solid principles and have that as part of your definition of done. The work isn't done until the complexity is as low as possible. And that will help us with the uncontrolled complexity issue. Depend on other forms of identifying and avoiding defects. Use templates, use checklists, use early reviews. Again, acceptance test-driven development, behavior-driven development show up again, model-driven development shows up again. For the avoiding the self-documenting code, make documentation that is value-added. Document the requirements of the software to expose the intent of the software, because the software doesn't tell you its intent. Document design to expose why the code looks the way it does more than how the code looks. Okay, so really quickly to summarize, I defined what success was. I talked about what typically happened in software projects. It's just too much money to ignore. We have to change things. As I said, it's just too much money to ignore. What are the top 5 causes? We talked about that, and what can you do about those top 5 causes? So let me summarize here. Software project success means finishing on time, on budget, delivering everything with appropriate quality. Team is stronger. Typical software projects perform quite poorly. They're late, they're over budget, they're under scope, abundant defects, and the economic impacts are just too much for us to be ignoring. We, as an industry, have to be doing a better job. The top 5 causes: vague, ambiguous, incomplete requirements, inadequate project management, uncontrolled complexity, overdependence on testing, code can't be self-documenting. We can address each one of these top 5 challenges effectively. So hopefully you're now aware of how poorly most software projects perform. You understand the biggest causes of software project difficulty. You understand that we can fix these problems, and that economically we need to fix these problems. If you want to track down any of the references, here are the references. How much money was spent comes here, and that's the QR code here will take you to the article that I got about how much money was spent on software. Okay, and so I'm pretty much done here. My email address, stevet@constructs.com. If you have any questions about what we talked about here, feel free to send me an email, and we can have a conversation about that. And so let me unshare my screen, and if we have any time for questions, I'd be happy to answer questions, but if we need to move on, I'm fine with that.
So, I think there is no question from the audience side. So,
Okay.
thank you, Steve, for your talk. It was nice talk, and
Thank you.
Thanks for accepting our invitation, and hope we will meet in person soon. So whenever you will be in India, then definitely we will have offline talk.
Yes, very definitely. Yes, thank you for the opportunity. And again, I'll send the slides to Dr. Anurag Singh, and he can distribute them, and we can just move on from
Oh, I
there. So
forgot
thank
to
you
tell
very much.
I am Anurag.
Oh, hi, Anurag. How are
Hi.
you doing?
Hi. So
Great.
so
Okay,
I think
so I'll send you-
it's late for you, or what's the time?
No, it's only 9:45 p.m. I'm in Vancouver, BC, Canada.
Okay. Thank you very much.
Thank you. Hope to see you all in the future. Goodbye.
With this, we now move to the parallel technical sessions scheduled from 10 a.m. to 11:30 a.m. After these sessions, we will break for high tea at 11:30 a.m. followed by the next round of technical sessions at 12 p.m. We will reassemble here at 2:30 p.m. for our next keynote session delivered by Dr. Sandeep Patil. Wishing everyone a productive session ahead and an enjoyable tea break later.
Vikas?